Hello and welcome. In this video, we're going to be discussing the insertion sort algorithm. So the video is going to be divided to three parts. The first part is understanding the mechanic behind this algorithm. So we're going to play a scenario to understand this insertion sort and how it functions. The second part is coding the insertion sort algorithm here. And the third part is trying to assess the performance of this algorithm by playing multiple scenarios that are already coded. So it's going to be more a discussion and just trying to understand and seeing the results. So let's start. So in order to solve this problem, we need two indexes. The first index is going to represent an index that's going to help us loop into the array. And the second index is going to help us sort the subarray pointed from here. So this position, if we have the index here, it's going to be like this. Each time we have this index, we're going to see if these two elements are not sorted, we need to sort them and then go on. So let's play this game. So here, for example, we have the index here. We're going to compare two of these elements. They are not sorted, then they need to switch or swap. And now no need to, we go here in this and we finish because it's 0. Then we increase this index and then we point at the same position, which means that we have another array to sort. By the way, this array is already sorted. So if we compare these two elements and we find that they are already sorted, no need to sort this. So we just increase the index and we follow again and we compare these two elements because this is already sorted and these are already organized, so no need to do anything here and we just carry on. Now we increment this index again, we follow and we see they are not sorted, they need to swap. So let's do it. So they swap and we decrement this index. They are not sorted, compare them, they are not sorted obviously, and we swap them. We decrement the index, we can see that they need to swap, we swap them, and now we decrement again and we compare and they are already sorted, no need to do anything. We need just to carry on and increment this index. Then we follow again. Because this array is now sorted, these two elements also are sorted, no need to do anything, we just carry on. So we point at the same position and then we do the same exact thing as we did before. These two elements, they are not sorted, we sort them and we decrement this index, we sort these two elements, 6, again, 2, 4, and again 3, and then we increase this index, we follow, this is already sorted, they are already sorted, so nothing to do in this subarray, we increment and we follow, this is already sorted and this is already sorted, so everything is sorted, and because we are at the end of the array, it means we have finished. So this is the mechanic behind this algorithm. So let's try to implement it. Now we have the function not implemented yet, it just takes an array as an input and we return it. So now we need to add code. So we're gonna need an indexed I that's gonna start by the value 1, as we said here. We start from here. And then we finish at the end of the array. So array length, and each time we increment I by 1. We have another index, let's call it j. It's going to be initialized all the time by the value of I, and then in order to swap these two elements, we need to have j bigger than 0 and end array at j smaller than array at j minus 1. And then we decrement the value of j. If this is all verified, then we need just to do something like swap the elements at the position j and j minus 1. For now, this function swap is not yet implemented, so we need to add it. So let's try to understand what we have just done. So we have an index that starts from position 1. We go through all the array, and we have another index that starts from I that represents the index that help us loop through the sub array that need to be organized, and we check did we finish or not, and we check if the two elements are not organized or not sorted, then we need to sort them by swapping them. So let's create this function. Swap. It's gonna take an array in the input and a position I and j that they need to swap. In order to do that, we need to create a temporary value that's gonna take the value of the array at I, the element at the position I, and then array of I needs to take the value of array of j, and then array of j needs to take temp. So this is the implementation. I already have some tests. Let's have a look at the tests. Tests, insertion, sort. So we create an input here, which is like, in this case, it's random numbers, like not organized at all. And then we call the function insertion sort that we import from source that we just implemented here. And then it returns to us a result, which is an array that should be sorted. So we expect that this array is going to be equal to this. As you can see, I just tried to sort these elements and put them here. Again, another scenario, which is the nearly sorted array. So this array looks like it's already sorted, but not quite, because we have this element that ruins all the sorting. So we do the same, and it should be returning this array. And the third scenario is the worst case, which is a reversed sorted array. So this should give us, so let's run these scenarios. So the test is failing. Let's see what is going on. Go back to the code and see what has happened. So we do a loop and oh, okay. So this is the problem. It's land th. All right. So now the tests are passing successfully, which is great. So I created a script. So I created a script here that's gonna simulate those scenarios. So we have here a function that's gonna generate a random array. Just give it the length of the array. It's gonna generate us an array with random numbers. We have a function that generates the worst case, which is the array is sorted in the wrong order, and the last scenario, which is the best case, which is an already ordered array. So we just like push ordered number to the array. And here what I do is I created a function that's gonna take a file name and the data generator callback, which means one of these functions, the tree. We have three. So we're gonna run the simulation by all these scenarios, 100 elements in the array till these numbers in the array. So this is n, which simulates how many elements we have in the array, and this is how many times we're gonna run the simulation for each of these numbers. So we're gonna do that. So you can see here. And each time we're gonna call the generator of the data, and we're gonna do the sorting. And here I calculated basically the time with these, how much time it takes to perform this operation. Once I finish, I just add the value here to the result, and I calculate and compute the average time of the operation. So for each time, we're gonna have 500 time repetition, and we calculate that here. And at the end, we're gonna run this simulation 3 times. So first time with the random generator, and we're gonna sort the data in this file. Again here with the second generator, the worst case, and here the best case. Once this is gonna run, it's gonna create to us some data that's gonna be stored in these files. So let's see how this is gonna be working. So run and start. So here I'm setting the Y label to result, the X label to number iterations, and I am plotting the results that are in these 3 files. Here in each file we have, this is going to be the X index and this is the Y index. The X index is going to indicate how many elements we have in the array. For example, here in this line 100 elements, this is the time spent in the processing. For 1200 elements, this is the time that we spent processing. So let's run this. So this is the graph that we have generated. We can see that the performance is exponential here. And we can also see that the worst case, this is the case of the worst case, which is much worse than for random data. And it is even much worse for almost sorted elements. So here when we have the array completely not sorted and in a reverse way, so it takes a lot of time to sort it because we need to iterate of each element and we need to skip none of these elements. Here in the other hand, we can see that it takes a little bit less time, but still it's quite expensive since it's exponential. And here it takes no time. So the insertion sort is quite efficient when the data is almost sorted. It is also quite efficient when we have not much data because the performance is quite similar. But once we have a lot of data and the data is not organized, is in a reverse in reverse order, then it's performing very badly and we should avoid it. So let's save these changes. I'm gonna put in the description the link for this repository where I host all this code, so you can have it if you like. If you have any suggestion to enhance these tutorials, just let me know in the comments, and if you did learn something today, please like the video and subscribe for more videos. Bye bye.